Good morning, everyone. So you have last 2 days, you have seen the flows and you have seen shock waves and solved the problems, why they form, all that, right? So and then importance of the shock wave, importance of like you need to know where they are. Their position is very important. So let's look at the experimental part, like how to visualize them, right? So one method is I'm going to talk about little about Schlieren imaging, which we are going to demonstrate in the afternoon session. So I'll just talk about a bit, give a brief glimpse of what it is and what to expect and what are the components and slight theory behind that. So just to give a little introduction, so usually like Schlieren imaging is used to change get the invisible density gradients. So right, so you have seen if there is a shock wave, so obviously before and after the shock there will be a, what are the things that changes? Pressure, temperature, so they change. Obviously there will be a change in the density, pressure, temperature. So any streaks appear is called Schlieren. So any streak, so you might have seen like a lot of cases, right? If there is a hot summer day or if something is hot, right, you can see that something is flickering on the other side. So there will be a density gradient. Because of that, whatever the light coming from the object will bend, right? So a density gradient because of the refractive index gradient, and that changes this. So again, the Schlieren images are generally used in so visualization, as you see that visualization of a shocks or any density gradient. So even or any density gradients can be caused by either pressure difference or temperature difference. So right, or even if there are any different species, right, so even that can cause, so even the temperature pressure are same, something just evaporating, right, evaporating liquid. So obviously the pressure and temperature are same, but there will be a density gradient because the concentration of species is different. So even that, so we can visualize it. So right, so if you look, we all said that okay, there is a density gradient and then because of that there is change in the refractive index. Then how do we relate these two? So right, so usually refractive index, you all know how do we define it, is a speed of light in vacuum to speed of light in a given medium, right? So is it, so C naught is a given medium, so C naught is, which is so vacuum, so which we all know 3 into 10 power minus 3 into 10 power 8 meters per second, and speed of light in any other transparent medium, which is C. So the transparent medium will be like what we have to image, right? So then like if you see the air, if you look at the difference, so it will be like a really a small difference. And then there is a Gladstone-Dale equation which relates this your refractive index to the density gradient. So for any gas medium, so n is a refractive index which we define. So that, so this n is a refractive index. So minus 1 is related to the density by constant called K. So right, so for the air that is 2.3 into 10 power minus 4. So if you draw, right, density versus n value, so if you can see that if the density changes twice, the refractive index change is really a small. So and again same thing, like if you plot in a logarithmic scale, you get much larger. So if you look at this, so even a density change in 100 times will cause only 2% change in, like 100 times, 2 orders of magnitude in density changes, 2% change in the refractive index. Now, so why we are discussing that is you have to capture this small changes, right? So you, whatever the system you want to build or measurement system should be so sensitive that it should capture this small in the change in the refractive indexes. So let's look at a little bit about like what happens if the light goes through this medium with the difference in the refractive index. So right, so let's take, so there is a light like wave coming in, and so this comes in, and assume that okay, this light ray is, there is a density gradient from, let's say this is x direction, y direction, and z direction, right? So there is a density gradient in y direction. So let's say, or n varies in y direction. So n is, let's say this is z1, and yeah, sorry, y1 here, and this is y2. So right, so let's say if this is y1, here refractive index is n1, here refractive index is n2. Let's say n1 is greater than n2. Take that, means at the bottom you have a large refractive index compared to the top. Then how do like if you look at the travel, how does the light travels, right? So because refractive index is small, it will travel more here, isn't it? And in the same medium, inhomogeneous medium, so here it will travel less because of the let's say if this is t equal to 0 and we have delta t, so this will end up like this. So there will be, so this in a medium, you take a starting point, and after delta t, so this will be like this, right? So if it is in the same medium, what happens, let's say now if you take the shock, so what happens is suddenly it is encountering a different density, there is a density gradient here. What happens if there is a change, sudden change in the refractive index? There will be a refraction of light, will bend a bit, right? Let's take that case. So then we come up with the, or we can now we can say that okay, so let's say this is z direction, right? So on an average, if let's say delta z, so this distance travel will be z2, this distance travel will be delta z1. So delta z2 will be how much it is? So in general, delta z will be c times delta t, right? So c times delta t. So which is nothing but c, we can write it in the form of refractive index c naught by n times delta t, right? So now, so from the same thing, we can write delta z2 as c naught by n2 delta t, and delta z1 is c naught by n1 delta t. So right, so this is how we can write. So now if this, so keeping this in mind, let's say if we have, so let's look at, let's say this, so light interacts, wavefront comes in, interact with it, and then there is a, so there is a reflection of this wave. So there will be at an angle. So if the medium was homogeneous, light would have come like this. So here if I take this as some average value of y, and then this as y1, this as y2, so as we said here, it will be c naught by n2 into delta t. Here it will be c naught by n1 into delta t. So now like without any variation, if this is the one, and with variation, so this angle, let's take it as a small angle, delta epsilon. I'll just use different color. So, and if I draw a parallel line here to this, so this angle and this angle will be, this also will be delta epsilon. So now we can find this delta epsilon, right? We need to find this delta epsilon. So from this we can write tan delta epsilon. Usually this is very small, since this is small, which is equivalent to delta epsilon, which is nothing but, so this length will be c naught by n2 in, okay, delta t minus c naught by n1 into delta t over this distance is y2 minus y1 is delta y. So if we take the average of this is like average or the mean value of mean value, so we can also write delta z as, so we can write or c times delta t as c naught by n, sorry, delta t, right, which is nothing but a delta z value. So right, so using this, or delta t is simply c naught by n times, so just taking this into n by c naught, sorry. So now if we put this delta t there and simplify this equation, so we can write delta epsilon as c naught by, like we have c naught by n2 and this delta t, so there we have delta t, we have, so what we have, n by c naught into delta z minus c naught by n1 into n by c naught delta z by delta y. So we can simplify this, right? So c naught will, all the places c naught will go, right? So we can simply write by, and then this n by n1 n2 times n1 minus n2 times delta y times delta z. So as delta y tends to 0 and delta z tends to 0, so we can write this equation. That means n1 tend to n and n2 also will tend to n. If you simplify this equation, this simply gives us 1 over n times, so this will be simply, so this we can write dn by, so this also we can write as d epsilon is dn by d epsilon by dz as dn by dy. So any change, this epsilon is nothing but the angle, d epsilon is the small angle it is deviating, so which gives, if we can find out this change in the angle, we can find out change in the like refractive index. So that is how, like, we need to eventually we need to find the change in the refractive index with respect to x. If it is x direction, it is x direction. If it is y direction, y direction. So we need to find any change in this. So it will not measure. We need to see that it is not going to measure the absolute value of n. So this method we can only get change in the refractive index with respect to any direction. If it is x direction, we can put it in the x direction. Yeah, so this is like, again, so again all that we put it here. So as we saw, like delta n is very small. We saw this, right? Delta n is very small, or so even large change in the density generally like will have a very small change in the epsilon value, so or that is the angle values. So we need to capture that. So now so whatever the method we use, so we need to capture this. So let's look at how light, what are the ways light interacts. So like this density based, these are all optical measurements because we use light to measure something. So if we have this, so then we can quantify these methods into, one is like all these are called optical methods based on the density. So if you look at like optical methods, so you can like density based ones. So because tomorrow we will see other optical diagnostic methods, so you can divide into different ways what we have. So one is based on the deflection of light, and other is, see, two things. One is you can measure the deflection, or because of change of refractive index, what is happening if there is a change in refractive index, light is going slow, right? So the velocity or speed of light is reducing. So then if you can measure the time delay also, like if I have two objects are there, one, I have transparent objects, one has higher density, one has lower density. Now I pass the light, so one, I can measure the deflection angle, and based on that I can tell some about it, or I can have how long it takes for the light to move, but for that you need like a really, but there are different ways, either that or once this light travels, so there will be and then you merge both of these beams. So because the travel time is different, there will be a phase difference between that, and you like if you allow them to join again, so there will be interference. You measure the interference patterns, and then based on that you can comment about these things. So this is the other in is based on the travel time. So right, so in the deflection of light, what we have is shadowgraphy, other is what we have is Schlieren, right? This method is called, I think, which we are not going to discuss, Mach gender interferometry. So we have this method. So this is used based on the interference. For that the setup is different. So they'll split the beam, one passes through via vacuum, one passes through the medium you measure, and then join them together. So based on the phase difference, there will be interference patterns. So here we are going to discuss about the shadowgraphy and Schlieren imaging. So main difference between the shadowgraphy is a simple, I think, which you encounter many times in day-to-day life. You can even do a small experiment after going home. So you take a vessel with a black bottom, or put some black paper in the vessel. That is good enough, I think. No need, it is difficult to get the vessels with black bottom, or if you have that, put water in it, put a small water drop, oil drop. So oil drop, it will form like, it will not mix with water, right? It will be like, so then flash your mobile light. You can clearly see there will be a, so you can see the oil drop pattern, shadow of the oil. It is simply like you put a light, you put an object, so this transparent medium, so the light will bend and focus on the other thing. So then the Schlieren is slightly bit more complex, I would say. So what you do is, you block the bent light. So we'll see in a moment. And that's the reason. So shadowgraphy captures, you have any second order, are sensitive to only second order gradients in the density. So right, whereas the Schlieren is first order. So we will come to that. So yeah, this is the like shadowgraphy and Schlieren. I just want to show this difference, because shadowgraphy we will see in other, like Friday's class also we will see that. So here you can see that. So this is a small detonator. This is experiments did at IASC. So where they used a small detonator, tube detonator, and ignited something at the tip, and you can clearly see that the Schlieren, you can capture the density gradient much well compared to the shadowgraphy. Shadowgraphy also there is like it can capture a bit, but Schlieren imaging, so these density gradients or finer details are captured, even small change the density. So with that, we'll just look at the little more details into the Schlieren, the Schlieren setup. So and then how they are arranged. So most common Schlieren arrangements what we have are, one is like, this is the simplest thing. You have a light source here and there is a small lens, and this light, it will focus into one place, and in between you put your medium, whatever you have, and then block the light which gets deflected using a knife edge, and that onto the camera. So that is one way. And the second one is, use instead of this, you can use two lenses to create one lens. Using one lens, you create a parallel beam, and that interacts with that. Again, you try to focus, and when you try to focus using the second lens, you could see that the one which bent will be blocked by a knife edge, and the one which goes straight will go. So that will increase the contrast. And the third one is, instead of using the lenses, so there are you can use what you call as a parabolic mirrors, like huge mirrors. Again, using that you can create a parallel beam, and then so have at the focal point you will have a knife edge, and this knife edge will exactly same like the deflected ones, it will block, and then you will have a image. So other one is, instead of two mirrors, you have a single mirror again, but you can see that the angle here you have to work is really small. So this is also one method. So instead of two mirrors, you can have a single spherical mirror. So these mirrors will create a parallel, these are called parabolic mirrors. You create a parallel beam. If you put a light source at the focal point, so then you will get a parallel beam. So these are the common types of Schlieren arrangements. So then what are the, again, so in this, the mirrors are the ones important. The surface finish of the mirrors, usually all the optics, you will have surface finish, right? So that has to be very good. So right, so because you need to capture very small gradients, there has to be really good. Usually it is measured in lambda, wavelength value. So how much deviation you can have if you work with a wavelength of light lambda. So total deviation or the surface imperfection you can have will be, let's say you are using 532 nanometer light, all you can have the variation in the mirror will be lambda by 4, lambda by 8, or 1 lambda. That means you can imagine that it has to be really perfect mirrors. So here the knife edge position is very important. So you can have a complete so because once the gets deflected, so you can put a circular aperture or use a knife edge. So if you, based on the knife edge, if you put it in a horizontal position, so you can see these images. Once we'll be demonstrating all that in the afternoon. So if you put in one side vertical, so you can see that this side it got blocked, this side it is still there. Horizontal is one way to put, so where you get these things blocked. and also positioning. If it is knife edge is very close to the mirror or the lens, you get a dark spot. If you correctly place, then only you get like a good illumination. Otherwise there will be a variation in the illumination. So, and then these measurements are very sensitive to like where you place this, the knife edge. So usually general relation is like this: if sensitivity of the Schlieren depends on the focal length of the mirror, and let's say if there is no this Schlieren medium, so whatever you want to measure, image is here, and with the medium we all saw that light bends and then it deflects and make the image slightly this different. If this is delta A, so the how much like original image you are, because this is the A value, so right, if I have original image here, so how much distance I am blocking the original one, so that is A. So if you block too much, like if you can block, if the A is small, sensitivity will increase. That is the difference. A is this distance, so if you block more than half or closer to, if you block it completely, the sensitivity will become good. And or you have a large focal length mirrors. So these are the two things you can keep in mind. You say that here you can see that, so if you have like 100% block of the original image, you get. So what are the typical applications we saw in the shock waves, right? Apart from that, this Schlieren imaging is used in many like other applications to get a qualitative information. So even in agriculture, this is in greenhouse. So in greenhouses, how the flow is going around any hot bodies or around the plant, if there is a temperature difference. I think afternoon we can see that even if you put your hand, you can see that thermal plume going because of the thermal gradient. Or from any, these are the shock waves, you have any projectiles. Here you can even see the flow, especially this is shock, this shock you can easily see. But if you look closely here, so boundary layer you can see, and that boundary layer transition from laminar to turbulent. So right, that also you can see. Another, this thing is like a hot solder iron. So these temperature gradients will be really small. Large density, associated density gradients will be small. Or kettle, now the steam is coming. So that is one thing. Or even in the HVAC systems, these are like heating ventilation. HVAC systems, we call it as heating, ventilation and air conditioning systems. There is a heater sitting here. How the flow goes, right? Let's say you want to design a like good heating system, so you need to have this all the hot air going all around, right? So those things also, this is in a solar heater. Or so even in a biomedical applications they use this kind of Schlieren can be used. This is in eye, so they can do small Schlieren imaging to get what is going. Or so this is like a dog's nose, like breathing from that. Or in a human also they do that. Sometimes people do have a problem with speech, all that, right? So when they talk, they can see that how the air coming out of their nose and mouth, and based on that they can see like where the problem is. So this is one application. Or even a manufacturing applications, like you have a torch, oxyacetylene torch welding, or plasma interaction with our plasma cuttings. Or even in this melt atomization, there is a method called thermal spraying, where you use high temperature metals, they use to create a powders, all that. So again, wherever there is a density gradient, and here this is from the nozzle, so here this is a liquid, and then you have a high temperature gases coming around it. So right, this, so I think so we did in our lab. So simultaneous measurement, this is like a simple backlight imaging, or you can consider this to be a closer to the shadowgraphy, because we are putting a light, taking the image, and then these drops are exploding. So you can see the difference here. If you see, just a flame is there, and here you can observe some hot gases. When this explodes, there will be a big cloud which is right? Here you can see the hot gases are. So observe the difference between these two. So simple backlight illumination imaging will not be able to capture all that. In the Schlieren, we should be able to capture any density, like let's say this case, so vapor ejections or hot gases, how far they go. So those things also we should be able to capture. So probably we can demonstrate this also in the afternoon. We can just put a drop. So this is about Schlieren, but then like here we are limited by all the Schlieren arrangement. We are limited by the size of the mirror, right? If I want to, let's say, capture like a very big thing, very big object, then my lens should be of that size, right? So otherwise we'll not be able to capture. I think the maximum lens size they have is about a meter, so where they captured earlier. So there is another small variation of this Schlieren method, which is called a background oriented Schlieren. It is nothing but like you have a pattern, and how much deviation, in simple terms, so what is the deviation in that pattern? Like you have a dotted pattern, you would have seen, right? Like if there is a some pattern on that cloth or something, you put a hot object, so there will be just like a mirage. You will have like something is on the road. You can see there when you're on a hot day, if you go, you can see the object on the other side is distorted a bit. Now we have a dotted pattern, and like this dot kind of a pattern, some pattern may not be a dotted pattern, there is some pattern. How much deviation is there in that pattern? So just like I think tomorrow we'll see about the PIV from that. So we measure this shift in the pattern. So based on that is called a cross correlation from the images, and from that we can estimate so density gradients, all that. So like these are like if there is a pattern, and then without any this thing, and then we can get the density gradients based on background oriented Schlieren. These are the images taken by NASA, so on these high speed projectiles or aircrafts, and then they use background oriented Schlieren. So good thing with the background oriented Schlieren is you need not set up any big lenses, and even the pattern also, you need not have always something like a speckle pattern behind or this dotted pattern behind. In the lab it is easy. Let's say if something is moving outside, so you can even use whatever there in the natural environment as in a nature as a background pattern. So something is, it should not be uniform, there should be some variation in the background. So just like here, there is a wind against a window, there is a small hot air gun, so from that you can get. So if you have a perfect dot pattern, you get much better contrast. Otherwise also like here, so there's a crop field here, and then they open a bonnet, there's a hot plumes from the engine, so you can capture that. So just like these things also, this is lab, in the lab they created a Schlieren, so you almost get a similar kind of, yeah, if you create in a lab you get like really good. But I think this is also workable images using the background oriented Schlieren method. So like this is just against a plant, a lot of plants are there, they created eggs, they can get the blast wave. So other variation is, so we all saw that Schlieren with a monochromatic light. If you can use a color light, what is the advantage of using the different color light? So you can pick up variations, some more variations really easily, like this shock waves, or so if you see that in the background the variations are slightly different, and you have variation in the densities slightly different. And so all we need to is you need to have a, either this thing you can use different color lights to illuminate, or have a prism so that it separates before the mirror. So these are the few things I just thought so we can discuss, because afternoon, so as I said, so we will have practical session where we will do Z type Schlieren imaging, So where you will be able to see all that, either small density gradient will be showing from hot plumes from a surface, and then this drops explosion, and then Mach cones. So right, morning and Mach cones interacting with this, and then so these are the things we'll be showing. So we'll stop here, right? So this is about a brief about Schlieren. These are the references I can share with you.